Hi everyone, thank you for joining. So in this video we're going to solve an interesting integer equation. So given that a, x, y and z are positive integers, we want to find the values of a, x, y and z such that it satisfies this equation. So it reminds us of Fermat's equation. It's just the order reversed. So Fermat's equation would read x to the a plus y to the a is equal to z to the a, something like that. But as you can see here, the order is reversed, right? So if you like to pause the video here and try it yourself first, then we could go over it together. So let's start off with exploiting the fact that the real numbers can be ordered. So we have positive integers here, so we can order them arbitrarily. Let's say x is less than or equal to y is less than or equal to z, right? So we've ordered them without loss of generality. This is arbitrary, okay? So now let's start with the given equation. We have a to the x plus a to the y is equal to a to the z. So that implies a to the x is equal to a to the z minus a to the y, and we can rewrite it as a to the x is equal to a to the x into a to the z minus x minus a to the y minus x, right? So since a and x are real, positive integers, so a, x they all are positive integers, but the point is a to the x cannot equal to 0, right? So in other words, we can divide both sides by a to the x. So we're going to have a to the z minus x minus a to the y minus x is equal to 1. Now notice we've ordered them such that x is less than or equal to y is less than or equal to z. So if y is greater than x, that implies that a, we will have a multiple of a on the right hand side, on the left hand side, so a times something is equal to 1. That implies a must divide 1. Yeah, but this is impossible. No positive integer except 1 can divide 1, right? So if you go back to the given equation, clearly a cannot be 1, because if a is 1, you have 1 to the x plus 1 to the y is equal to 1 to the z, but whatever x, y, z are, we have 2 is equal to 1, yeah? So a cannot be 1, and therefore the claim that a divides 1 is literally impossible, right? So a cannot be 1. So based on our ordering here, we said x is less than or equal to y, or in other words, y is greater than or equal to y. X, since y cannot be greater than x, otherwise we run into a contradiction. That means we must have y is equal to x. And if y is equal to x, this equation boils down to we have a to the z minus x minus a to the y minus x is just 0 if y is equal to x. So we have a to the 0 is equal to 1. That implies a to the z minus x is equal to 2, right? And this is the equation now we want to solve. We know a is a positive integer. Z and x are also positive integer. So as we can see that if we have a is equal to 2 and z minus x is equal to 1, we have a solution to this equation, right? This means that we've obtained all the solutions to this equation. That is, a is equal to 2, x is equal to y, and z is equal to x plus 1, right? So this is the solution. Now let's test this solution. Well, obviously, if a is equal to 2, if you have 2 to the x plus 2 to the y is equal to 2 to the z, clearly implies if x is equal to y, you have 2 to the x plus 2 to the x is equal to 2 to the x plus 1. Yeah, which is obviously true for positive. We have positive integer x there. So in other words, if x is equal to 1, since x is a positive integer, notice that 2 to the 1, when x is equal to 1, you have 2 to the 1 is equal to 2 squared. So we have 4 is equal to 4, x is equal to 2. We have 2 squared plus 2 squared is equal to 2 cubed. X is equal to 3, 2 cube plus 2 cube is equal to 2 to the 4. and so on. As you can see that this will solve the equation, right? Okay, so I hope you enjoyed it. I hope you found it interesting. Thank you very much for joining, and I look forward to seeing you in my future videos. Thank you.